All right, didn't get any emails, didn't get any comments through Teams, so I'm going to leave it up for about 5-10 minutes. If you got questions, type in the chat. I see people waiting, so I'm guessing there are questions, but there's like a minute lag in this, the way I've got this set up right now. So again, please feel free to ask your questions. These are office hours, they are not lectures, so you're going to have to present questions. Manipulating equilibrium constants. Okay, so two aspects of this. Come on, Blackboard. One is just simply how you're entering it into WebAssign. The other is like fundamentally what you're doing. So let's say acid-base reactions are the easiest ones to do this way. And that's why you're going to see so many examples referring to acid-base, just because they're the easiest ones to demonstrate. So let's say I have the reaction H2O goes back and forth to H plus and OH minus. So I got liquid, AQ, AQ, and this is Ka, and this is Kw. And I want to know what if I switch this to, actually let me do two here. What if I want to switch this to basic conditions? So I want to know the equilibrium constant if I put two hydroxides on this side and pour into water. And so what I can do is I can subtract this reaction twice. So when it comes to adding and subtracting reactions, it's going to work a lot like algebra. So if I had this equation, let's say this is A equals 2B plus C, and then we've got D equals 2B plus, or B plus E, and I want to eliminate B from both equations, what I would do is I would subtract this equation twice. So I get A minus 2D equals 2B minus 2B plus C minus 2E, and then the rule here is that everything has to be positive, so I would rearrange it. I bring the 2E over here, so I get A plus 2E equals, 2B's cancel out, 2D plus C. In this case, D is water, so we got two waters, E is hydroxide, and that's how it works. So when we put a subtractor reaction, that's the same thing as reversing it. So if I were to subtract this reaction, I'd have H plus OH minus goes back and forth to H2O. And if I want to get rid of both pluses, both H pluses, I would do it twice. So that would give me 2, 2, and 2. And when I add these together, the H pluses cancel out, and I get H2O SO4 plus 2 hydroxide goes back and forth to 2 H2O plus SO4 minus 2. So that's fundamentally what we're doing in adding subtracting reactions. What happens to their equilibrium constants? Well, the short answer is if we add this and we subtract it twice, all we're going to do is multiply Ka times Kw to the negative 2. But there's a proof for this, and this is the proof I prefer to do when we do in person, where we actually go through and show, because a bad habit students will get into is they will sit back and say, well, if I add the first reaction and subtract the second reaction, that's my new equilibrium constant. The problem is this doesn't make any sense. And the way it doesn't make any sense is that equilibrium constants always have to be positive. So they're in principle, if you subtract reactions, there's a way to get a negative equilibrium constant. But the other way to look at it as is, so let's say I take the same reaction. out Kw, but I'm going to write out Kw in terms of Q. So Kw here is concentration of H plus, concentration of OH minus. Now let's say I double this reaction. So I make it 2 H2O goes back and forth to 2H plus 2 OH minus. And I ask you, not knowing anything, write out the new equilibrium constant. So you say, well, K nu is H plus squared OH minus squared, because I've got the concentrations here and I raise them to their respective powers. So if we look at K nu versus Kw, K nu doesn't equal Kw plus Kw, because that would be 2 times concentration of H plus concentration of OH minus. What it looks like is Kw squared. And so this is the pretty quick and dirty proof to show that when you add and subtract reactions, you don't add and subtract their equilibrium constants. You're actually raising them to their powers. So the easiest way to figure out the new equilibrium constant is look at the algebra you use to add and subtract the reactions. So to get this to H2SO4 plus 2OH minus goes back and forth to 2H2O plus SO4 minus 2. And I've got Ka and Kw. I'm adding this reaction and subtracting this one twice. My nu is all the equilibrium constants multiplied together, multiplied, raised to the powers that you're multiplying them by. So since Ka, we're taking it once, Kw, we're subtracting it. Your new K nu is Ka times Kw to the negative 2. Now, in terms of the homework, sorry, I gotta bring it up. Question is manipulating equilibrium constants. So I'll bring up the homework on the desktop. So the first one says, just never done that before. What would be the final expression of Kq if the following two reactions are together? Well, if you're adding together, it's K1 times K2, each of them raised to the first power. So that's how you get that answer. For the second one, what would be the expression of Kq if the second reaction is subtracted from the first reaction? Well, the first reaction, K1, we're going to subtract the second reaction, K2, so it's K1 divided by K2. So it's K1 times K2 to the negative 1 power, which is just K1 over K2. It's supposed to randomize these answers. I don't know why it's showing them all as the first answers. Third question, what would be the final expression Kq if the second reaction is subtracted from twice the first reaction? So you've got K1, we're going to double it, so it's going to be K1 squared subtracted by the second reaction. It's going to be K2 to the negative 1 power, so that's K1 squared over K2. For 4, Kq twice the second reaction subtracted from the first reaction. First reaction is raised to the first power. We're subtracting the second reaction, that's K2 to the negative 2 power. So it's honestly very easy to figure out the new equilibrium constant. The thing is to keep in mind is that even though you're adding and subtracting reactions, you're multiplying all the equilibrium constants. Again, there are proofs for this that make it a bit more intuitive. They're just kind of hard to see. But you never add and subtract equilibrium constants. There's no physical meaning behind that. There's a much more rigorous proof that explains it much better, but you don't need to worry about it at this level. So I'm going to move on to the next question, but if you still got questions about that topic, just feel free to ask it again, or just start adding questions to the comments. Had questions about the homework for free energy changes in Q as well as concentrations from K at Q. So free energy changes from Q. So I like finishing up on this material for the free expressions from Q because it really is the easiest part of this material. So you get a discussion board this week that's actually these questions here, and it says they all use the same formula. Delta G equals delta G naught plus RT ln of Q. And Q here is going to be some function of concentrations. So these are really the only two formulas you use. Now I asked on the discussion board, how do you know that you're not supposed to solve for the equilibrium constant? So let's take a step back here. Delta G is the free energy change at reference conditions. And the reference conditions here are 1 molarity for Q. So Q equals 1. So if Q equals 1, RT ln of Q is 0, because ln of 1 is 0. So when Q equals 1, delta G equals delta G naught. The point of this equation is that not everything is at reference conditions. We can definitely change the temperature and we can change the concentrations. But at equilibrium, Q equals KQ, which is e to the minus delta G naught over RT. So if we put in that expression for Q, delta G equals delta G naught plus RT ln of Q, but it's RT and the ln of this is minus delta G naught over RT. So our RT's disappear and we get delta G equals 0. So at equilibrium, delta G equals 0. And the reason it equals 0 is that fundamentally there's no preference for forward or reverse reactions. At equilibrium, the rate of the forward reaction equals the rate of the reverse. So for delta G to be non-zero, it means that we've either got too many products or too many reactants relative to equilibrium. So if you're being asked to find delta G with Q, inherently it has to not be at equilibrium. Otherwise, you're just going to have this condition, delta G equals 0. That's always true at equilibrium. So backing up, what you're going to find with all of these problems for finding delta G with Q is a reaction and trying to find the delta G. So you're just going to write out Q as you normally would. So the first problem here, you go to the homework question 1. Following reactions, delta G naught is 164. Temperature 75 degrees C. You need to convert that Kelvin. So 75 plus 273. R is 0.008314, and you're given that calcium chloride is 0.2 molar, sodium phosphite is 0.4 molar, and we'll talk about it. Sometimes I'll give you the mass of the solids. So Q here is just calcium to the third power and phosphite to the second power. So our phosphite here is 0.4 molar and calcium chloride here is 0.2 molar. And you say, well, that's calcium chloride, it's not calcium plus 2. That's because you can't buy Ca plus 2. You can't buy that in the store. All cations have to have an anion. They have to be ionically neutral for you to use them. So if you go back to the solubility rules, and that's why those pop up in the notes, chloride and sodium solubilize the calcium and the phosphite. So when we mix this together, calcium phosphite is going to precipitate back out. But we can't just say calcium plus 2 in phosphate PO4 minus 3 because those don't exist on a shelf. We have to have the chlorine and the sodium there so we can actually buy it. You can buy sodium phosphate. You can buy calcium chloride. Calcium chloride is just rock salt. So we plug these in. We'll get a number. In this case, the number 0.00128. And then we just stick this number in for Q and solve for the delta G. So these problems really are just an exercise of writing Q out correctly and then plugging the numbers in the appropriate place. Now, what you're going to find, particularly in the packets, it will give you mass. So it may say 1 gram of calcium phosphate. Here's the thing is that calcium phosphate doesn't show up in this expression for Q. And this is kind of a way of assessing if students are genuinely understanding what's going on or if they're just kind of like trying to plug and chug really hard. So if you look in the discussion packets, it'll sit back and say, okay, there's like 12 grams of calcium phosphate, and students will convert to moles, and they'll somehow try to get molarity out of it, which you can't do because it doesn't give you any volumes. Calcium phosphate, the solids, and any pure liquids do not appear in the expression for Q. It's useless information. Now, if you're doing what the problem is telling you to do, if you're working with the concentrations and applying Q correctly, you'll know that's just kind of distractor information. But if you don't understand what's going on, there's a temptation to apply this information even though it really doesn't have application to what you're doing. All right, concentrations from KEQ. So if you're being asked to find things at equilibrium conditions, always you need three things. You need your reaction, you need your expression for Q, and you need your IC table. There is no way around this. So I'm going to go back to the homework and we'll work the first problem. Oh wow, those are really easy problems. Anyway, concentrations from KQ. So here it gives you this reaction, H2C2O4, looks like oxalate. Goes back and forth to H plus AQ plus HC2O4 minus 1 AQ. And it asks you, gives you that the Ka here equals 0.0590, and you're given that the concentration of H2C2O4 is 0.1 molar, but you're not given any other information. So you've got the first thing, you've got the reaction, and we need our expression for Q. So Q here is H plus HC2O4 minus 1 all over H2C2O4. The last component we need is the IC table. We have H2C2O4, H plus, and HC2O4 minus 1. So I here is the initial concentration. So if you're not given initial concentration, the assumption here is 0. So we're given 0.1, H plus is 0, and HC2O4 is 0. The changes, it's always the reaction coefficient times the extent of reaction. So each of these have a 1, so they're going to be 1 times. For the reactants, it's going to be negative. For the products, it's going to be positive. E rho here is literally I plus C. So here we have 0.1 minus X, X, and X. And E here is the numerical row. So at this point, we filled out the table as best we can. The problem is asking you what is the concentration of H plus. So you're looking for this row here. But the thing is that the numeric and the algebraic rows equal each other. So those two E rows here, this is going to equal X. This is going to be equal 0.1 minus X, and this is going to be equal to X. So X is the only variable here. To solve the problem, we have the condition that we're at equilibrium, so Ka or KQ equals Q. And since we don't know the numerical row, we can enter in the algebraic row. So the concentration here of X is H plus, H2SO4 is X, and 0.1 minus X. And now we have an expression. We have 0.0590 equals 0.1 minus X over X. I'm going to keep this as Ka, just to make my life easy. So I can rearrange 0.1 times Ka minus Kax equals X squared. So X squared plus Kax minus 0.1 times Ka equals 0. Now I can just use the quadratic formula and I can solve for X. X in this case is going to equal, you're going to get two roots. The one that works is 0.0528. The way you can tell which root is the correct root, in this case it's really easy. You're going to get a positive and a negative root. Obviously the concentration can't be negative, so we have to work with positive roots, but in general you're looking for the ones that only give you concentrations as positives. So it doesn't matter what type of problem you're solving, this will always be how you approach it. So for this homework, you're solving for the final E row here. You're looking for a concentration. So odds are what you're going to have to solve for here is the extent of reactions. If we were to switch to another problem, So another homework is finding KQ from concentrations. Where KQ from concentrations. Just a minute. So in the first homework problem, it gives you the reaction iron 3 hydroxide, FeOH3 solid goes back and forth to Fe plus 3 AQ plus 3 hydroxide AQ, and it asks you to find KQ. So in this case, this is what we want to find. Well, we've got our expression for Q. It's concentration of Fe plus 3, concentration of hydroxide cubed. We've got FeOH, 3 Fe plus 3, 3 hydroxide. Because the hydroxide here is a solid, we don't have to worry about it. We're not given any initial concentrations, but you're told at equilibrium the concentration of hydroxide, should be a 3 there, is 5.89 times 10 to the negative 10. Changes here are plus x and plus 3x. So at equilibrium, we have x and 3x. Now, the thing is that these two rows equal each other. So we get that 3x here equals 5.89 times 10 to the negative 10. So x is just this number divided by 3. So 1. Divided by 3, 8, 9, 7, 6 times 10 to the negative 10. So now we set KQ equal to Q because we're at equilibrium. So KQ equals x times 3x cubed. I'm just going to pull off this row. And I know that x equals 1.69 times 10 to the negative 10, so I can just plug it in. In this case, you'll get 4 times 10 to the negative 38. So it doesn't matter for all these equilibrium problems, it's always the same approach. Set up your IC table, set up your equilibrium expression, set up your expression for Q, plug in as much information as you have. If you're solving for KEQ, odds are you're going to use the numerical row. If you're solving for a final concentration, odds are you're going to use the algebraic row when you plug in your expression for Q. But from there, you just solve. All right. Could you approach the problems on 18 applying equilibrium expressions on the packets? So let me bring up the packets. And alas, I need to download them. Got the packet. I'll give it a minute to finish loading. Page 18. Man, these packets are long. I'm getting there. Navigation pane. All right, so for the applying the equilibrium expressions, this is kind of just what the homework is, just a little bit more beefed up. So in all of these, it's some reaction. It's an acid-base reaction, and you're trying to decide what to do with the water reaction to make the acid go away in the problem. So we'll skip the first one. That one's pretty easy. And we'll go to the last one, the phosphate. And it gives you the KQ equals 4.45, 10 to the 20. This is also setting us up for the next test, by the way, which is very acid-base chemistry. So I'll get to that question next. So in terms of how you convert this, whether or not you add or subtract this reaction depends on if the H plus is on the left or the right. So if the H plus is on the left, you're going to add this reaction. If the H plus is on the right, you're going to subtract it, because subtracting it basically flips the reaction. And you want to add it until all the H pluses are gone. So pretty much this number here is going to be whatever you add or subtract by. And then the equilibrium constant here is Kw. So our new equilibrium station, Kq, is just K, the original Kq, times Kw raised to whatever power we had to add or subtract the reaction. In this case, we're adding it 3 times, so it's K4 times Kw raised to the third power. Now, Kw is a physical constant. It's 1 times 10 to the negative 14. So I think the packets actually give you the values for that, but that's all you're doing for those. So for that fourth reaction, you're going to add it 3 times. For the third reaction, the H2CO3, you're going to subtract the water reaction twice, so it's going to be K3 divided by Kw squared. But that's all those problems are. I'm going to get back to the common ion effect. Quick question, what is the difference between Gibbs free energy and Gibbs free energy not? So the delta G naught versus the delta G. So delta G naught has a very rigid definition. This is the free energy change at 1 atmosphere, 25 degrees C, and 1 molar aqueous in gas. And then we have a definition for the liquids and, for liquids and solids, it's the concentration of whatever that liquid or solid is at 25 degrees C in 1 atmosphere. This cancels out the activity in the full expression for Q. So delta G here is at reference. Unfortunately, most of the world does not operate at reference conditions. So the delta G here is delta G naught plus a correction. And this correction gets us away from the 25 degrees C, it gets us away from 1 atmosphere, it gets us away from the reference concentrations. So that's where that RT LQ comes from, is that it's simply just a correction term. If you're not really at those conditions, you have to correct for it. Why does K have a 4 subscript? Because it's the 4th problem. So if you look on page 18 in the problems, or it's actually page 15, the first reaction is K1, the second reaction is K2, third reaction is K3, fourth reaction is K4. It's the 4th reaction. It just makes it easier to talk about which reaction we're on. All right, common ion effects, problems on page 24. Definitely not that one. So page 21 on the problems. How would adding base affect the following two reactions? How could you derive the second reaction? How could you derive the second reaction using the first reaction? And how could you derive the third reaction using only the first reaction? So I'll bring those problems up just to make them easier to see. So for the first one, how would adding a base affect the following reaction? Let's make it a little bit bigger for you to see at home. Well, if we look at the third reaction, that's hydroxide, that's our base. So if we add this, we'll produce more aluminum hydroxide. But producing more aluminum hydroxide will further drive the formation of calcium hydroxide, because the common ion here is the aluminum hydroxide. So because we're increasing this hydroxide concentration, we're increasing the amount of aluminum hydroxide. By increasing the amount of aluminum hydroxide, we're going to remove the calcium ions because we're driving the forward reaction, and we're going to form more calcium hydroxide. And this is going to be kind of a weird feedback loop because that's going to increase this concentration, which will further drive this. But as a first pass, because aluminum hydroxide is the common ion, adding more hydroxide forms more of the aluminum hydroxide, which drives more calcium hydroxide formation. For the second one, how could you drive the second reaction forward using only the first reaction? Well, the common ion here is calcium. So if we want to drive the second reaction, we want to make this one go forward, what we need to do is remove the calcium. That's Le Chatelier's principle, removing products drives the forward reaction. So the way we could do that, since we only have one lever up here, is add more ammonia, the NH3. So by adding more NH3, we remove the calcium plus 2 to form the calcium ammonium complex. By removing the calcium plus 2, we reduce its concentration down here, and that'll solubilize more of the calcium hydroxide. This is actually what's done in practice to remove hard water stains. If you add a little bit of ammonia, this is actually the reaction that goes on. The ammonia complexes with the calcium. Because it's removing the calcium, this reaction goes forward, and that gets rid of the water spots. Last one, how could you drive the third reaction forward using only the first reaction? So here we actually have two common ions. So we've got calcium plus, and the other common ion here is the NH3AQ. So we only have one choice here. One is to increase the gas phase ammonia. The other is to increase the pressure, and I think that's more what it's going for with this problem is saying if you increase the pressure of ammonia, so you compress this system, you'll drive more aqueous ammonia. More aqueous ammonia will remove more calcium to form this calcium complex. And then by removing the calcium plus 2, that's how you drive the third reaction. Does Kp, Ka, etc. change anything other than just descriptive? It's just descriptive. They are special cases of KQ. So Ka in this case refers to a weak acid dissociation. Kb refers to a specific base dissociation. They all obey the exact same rules of KQs. We just deal with them enough that we like to specify them. It's kind of a shorthand to say that if you're working with Kw, you're working with the auto dissociation of water. So there's no kind of guessing. If you say KQ, every equilibrium reaction has a KQ. It's not clear which one you're talking about. But if you say something like KSP, we know the form of the equilibrium. So it's just kind of a shorthand. But as far as approaches goes to solving them, it's still the same thing. Set up your reaction, set up your Q, set up your IC table, and then figure out what variable you're hunting down. Yeah, you're welcome, Dia. All right, other questions out there? Problem 4, test 3, Le Chatelier's principle. So what would happen is sulfite was added to the following reaction. So what would happen if you add this? So if you're adding a product, you're going to drive the reverse reaction. This means that the amount of calcium sulfate is going to increase and the amount of calcium here is going to decrease because we're going to have to remove it, drive the reverse reaction in order to get rid of it. So you got 4 answers here. More calcium sulfite would be formed. That's what happens. More calcium sulfite would dissolve. That doesn't make sense because we're driving the reverse reaction. So that answer can't work. The concentration of calcium plus 2 would increase. That also doesn't make sense because we're driving the reverse reaction and removing the calcium. There would be no effect on the reaction. The sulfite is there, so we do expect an effect on the reaction. So process of elimination, calcium sulfite would dissolve. That doesn't make sense. It's the wrong direction. Concentration of calcium would increase. Doesn't make sense. Wrong direction. There would be no effect. Doesn't make sense. We know we're adding something. And the reason why calcium sulfite would be formed is we are driving the reverse. So luckily these live streams, so someone just texted, posted that their power went out. Luckily these are all recorded, so if you miss anything, you can play it back now, or if you want to, you can go to the course website. There's a link that shows you all the old live streams, so you can go back and play this as you need to. Now that said, I've just said that, the power's still on here. Let's make sure we're still, yep, still recording. Why does the concentration decrease for the previous problem? So the reason it decreases is that the only thing we've done is we've increased this concentration. So when we say we drive the reverse reaction, we're reacting everything off this side. So right at equilibrium, these started out in the right ratios. Now this number's too high. So what's going to happen is that the calcium and the sulfite are going to recombine to form the calcium sulfite. But it's 1-to-1. So as we're removing the sulfite to compensate for the sulfite we added, we're having to remove the calcium at the same time. So we can't selectively eliminate one thing off of one side of reaction. If we're going to go backwards, both of these have to react. If we're going to go forward, this one's going to have to react. So that's why they appear on the same side. You're welcome. The typo is forever immortalized, assuming YouTube never actually goes through and purges this old stuff. What are the questions out there? Which of the following salts would be ideal for removing calcium from hard water? Gotta find it first. So if we've got calcium in hard water, it's Ca plus 2. And we want to add something that will end up giving us some calcium salts. So we'll say X solid. So we got a few options up here. Sodium sulfite, lithium chloride, barium chloride, sodium fluoride, magnesium fluoride, lithium phosphite, cesium phosphate. And that's it. And the question is, which one of these would be best? Which of these would be good for removing the hard water? So there's two things we need to consider. First of all, calcium is a cation, which means we're looking at the anion. So X here is going to be some anion. And in all these cases, we got sulfite, chlorine, fluoride, phosphate, phosphite, fluoride, and chloride. Now, question is, does it form something that's insoluble with calcium? So what we have to look at is the solubility rules. So the solubility rules, we're not going to concern ourselves with cations, but we are going to concern ourselves with the anions. So nitrate, acetate, chlorate. Sulfate will react with calcium to form a solid, so sulfate would be a viable option for removing it. And then, but chlorine, bromine, iodine, those only, chloride, bromide, iodide, only form insoluble salts with silver, lead, and mercury. So in terms of forming a solid, sodium sulfate would work, but lithium chloride, calcium chloride is soluble in water. Magnesium fluoride, there's a possibility. Calcium phosphate, phosphate would definitely be insoluble. Barium chloride wouldn't work. Fluoride here would probably work, and then we got our phosphide. But the second thing to consider here is that it doesn't do you any good if it doesn't dissolve in water. So let's say you chunked a whole bunch of magnesium fluoride into the water. Well, magnesium fluoride is insoluble in water. It doesn't have a solubility rule. And because, sorry, clean off the mat here. Because it's insoluble in water, this wouldn't do anything. It would just sit there and the calcium would float in the water. So this fails not because of the fluoride, but because the magnesium doesn't have a solubility rule with it. Sodium does though. So we put sodium fluoride in water, we're going to introduce the fluoride ion, and that will react to give us calcium fluoride, which is insoluble in water. It'll crash out. Lithium phosphite, lithium has a solubility rule, so this would work. And then cesium has a solubility rule, so that would work. So it's two factors. Which of these contain an anion that would react with calcium in water to give you an insoluble salt? So there's your insolubility rules. And then of the ones that have an anion that would work, how many of them are actually soluble in water? Because if they're not soluble in water, they're not going to do you any good in terms of removing the calcium. Now, to assuage any concerns, like I don't think there's any questions like that on the exam. It's more to get you thinking harder about what's actually going on with these double substitution reactions, as well as just kind of applying the solubility rules. Yeah, you're welcome. Not meant to be super hard, but more just kind of applying those rules and seeing how those rules will be used in practice. All right, not really seeing any concurrent viewers right now, so we'll give it a few more minutes, and then if there's no more questions, I'll take off. Again, don't forget you've got your exam this weekend, so do email me if you have any issues, particularly if the power goes out on you in the middle of the exam. This is definitely something I can see on my end where I'll get some weird log off information. But do contact me. Don't wait till Sunday. If you can, go ahead and get it taken early. The big thing here is that if there's IT issues Sunday afternoon, there's really not that much I can do for you. Putting that out there. But other than that, this week is the withdrawal week. So if you want to withdraw without penalty to your GPA, so you just want a W, not a WW, not a WF, email me Monday. I will try to have all the exams graded and posted Monday midday. If you have concerns about your grade, hold off doing the discussion boards. There's really no penalty for not doing the discussion boards and doing them late. But if you're kind of questioning, it depends on what I get on the third exam, wait. If you see your third exam and grade and go, I really want to drop the course, shoot me an email by Monday afternoon. Tuesday, I'm going to do all the attendance because I'm just going to take a break after doing all that grading. I just need a day off, or at least from administrative stuff. And I can try to get you withdrawn before the WWF date so it doesn't affect your GPA. But again, if you wait till like Tuesday or Thursday next week, nothing I can do for you. You're already past that withdrawal date. But definitely Monday, keep an eye out for your grades. If you see your grades and go, yep, I want to stick with the class, no need to follow up. But if you sit back and say, I need to drop it, let me know so I can get that paperwork processed before we cross the WWF limit. All right, so no further questions. I'll go ahead and sign off. As always, please feel free to email and reach out, particularly with these live streams. Email me in advance if you can't make the live streams, and I'll definitely answer your questions at the start. All right, thanks for coming, and I'll see you all next week.